It is a really exciting time at the moment to be involved in the study of the sun, other stars, and also as well the search for planets around other stars. And this is being driven by a new generation of satellite and telescope observations of unprecedented quality and scope. So what I'm going to be talking about this morning is the influence that the sun has on us here on Earth through its changing outputs and emissions, and by extension, the influence that other stars have on their local environments as well, including any planets they may host. Now, in order to be able to understand those changing outputs and emissions, I'll explain how being able to understanding the processes that take place inside stars is crucial to that. Now, when you look up at the night sky, you might have wondered how many of those stars actually host planets, just like the planets in our solar system. And how many of those planets might potentially be habitable, like the precious planet we live on? Is there some special combination of characteristics that a star must possess in order to be able to increase the probability that it might host a habitable planet? Or are some stars just too dangerous for the planets they may host? And also as well, how common is our solar system? And can we get insights on space weather, the changing outputs and emissions from the sun, which ultimately have their origins in processes that take place inside stars? Now, the sun is one of billions of stars in the galaxy. Stars are the building blocks of the galaxy, and they help to drive its evolution. But also as well, of course, they provide harbors for planets. They host planets, and as well provide crucial sources of energy for giving conditions that can maybe support life on those planets. Now, stars are huge, vast balls of hot ionized gas. This is an image of our star, the sun. Stars are comprised mainly of hydrogen and helium gas, with a smattering of elements that are heavier than that. And throughout most of their lives, they're powered by nuclear fusion reactions taking place in their cores. Now, the sun is in many respects a Rosetta Stone for stellar astrophysics because it provides us with an opportunity to study up close a star that we just cannot do by other means with, for other stars. Just simply being able to resolve the surface of the sun in ways we cannot do for other stars. And what that does is it enables us to better understand, of course, the evolution of the sun itself, its past and its future, but also as well, that provides a bedrock for our understanding of stellar evolution in general and the life cycles of other stars. So this is something I will come back to. But also as well, there is relevance for us here on Earth in our technological society. So the sun affects its local environment, including the near-Earth environment and the Earth, through its changing outputs and emissions. And these are related to what we call the sun's activity and the presence of magnetic fields on the sun. So the sun produces huge quantities or releases huge quantities of charged particles in what's called its solar wind, and also through massive discrete events that are called coronal mass ejections. Now, these emissions can travel through what we call the heliosphere to the Earth, and they can interact with the near-Earth environment, including the Earth's magnetic field. So that's shown schematically on this image here, where we've got the sun on the left, producing its emissions, and then on the right, we've got the Earth and its magnetic field. Now, when those emissions interact with the Earth's magnetic field, we get the beautiful phenomena of the northern and southern lights, the aurora borealis and the aurora australis. But also as well, there are practical implications for our society here on Earth. So those emissions can affect global communications. They can knock out communication satellites. They can also as well lead to power or current surges in power grids on the Earth. So being able to predict the occurrence of these events, so stuff we call space weather, is really important. And this is linked to, again, the outputs and emissions from the sun and our ability to maybe be able to predict these events when they might occur. And believe it or not, the risks from space weather now feature on the government's National Risk Register. Now, the sun's outputs and emissions do change over time. They aren't the same all the time, and most conspicuously, they change on an 11-year timescale, the sun's solar cycle. This image here is showing, it's a false color image, showing emission produced by hot gas in the atmosphere of the sun that's been energized by this activity or magnetic fields. So on the left, we've got an image of the sun when it's quite quiescent, and it's at a low point in its solar activity cycle. The cycle lasts 11 years, so 5.5 years later, we see something like the image on the right-hand side when the sun is much more active. Now, no one 11-year cycle is like another, and actually the cycle that is just finishing at the moment has been the weakest for over 100 years. So there is some speculation about whether the sun possibly might be leaving a period that we've called the modern grand maximum, when we've had a succession of these 11-year cycles where the sun has been quite active. So the challenge for us then is to be able to predict the occurrence of these events at the Earth. We have to track back then to processes that happen at the surface of the sun, which are seeded by things happening inside the sun, and that's something I'll come back to. But there are also wider implications for thinking about these issues for other stars, and that's because we are discovering literally thousands of planets orbiting other sun-like stars in our galaxy. So the NASA Kepler mission has discovered around about 4,000 or 5,000 planets orbiting other sun-like stars in our cosmic backyard. We know now that planets are very common, in particular small rocky planets like the Earth. And so clearly we want to be able to better understand how those stars influence their local environments, including their planets. Now, some of the planets that are being discovered might lie in the so-called Goldilocks zone around their stars. So this is the region that's not too hot, not too cold, but maybe just right for there to be liquid water on the surface of these bodies and for maybe life to have a chance to develop. Now, in order to understand where that zone lies around a star, you have to know as much about your star as you can. So building up a detailed portrait of whether or not we've discovered systems that might have planets capable of supporting life really rests on knowing as much about the star as possible. So it really is a case of to know thy planet, one must know thy star. So for example, fixing the Goldilocks zone in the first place, we need to know how intrinsically bright the star is, so how hot it is and how big it is. If we think we have a small rocky planet maybe in the habitable zone of the star, we might then want to know how old the planet is, and that we can get from the age of the star. And it's important to remember that the vast majority of planets that we're discovering around other stars have been discovered indirectly from the effect that they have on the light that we receive from the star. So again, this all tracks back. If we don't know or don't have a detailed picture of the star, there's no way we can build up a detailed portrait of these planets. And another crucial factor then is understanding the activity of these stars. So we know that as stars, when stars are very young, they tend to be more active. They tend to produce more of these charged particle emissions, which makes things a little bit more dangerous for the planets around them. So we'd like to be able to better understand how those emissions change as stars age, but also as well how they change with the type of the star. Now, all of these processes are basically seeded by things happening inside the star, underneath the surface of the star. And in particular, they're linked to magnetic fields, and they're linked to patterns of rotation inside the star, which mold and evolve and shape these magnetic fields that then burst through the surface of the star and give rise to the events and the releases of charged particles that we've been talking about. So if we want to understand the first link in the chain, the events that ultimately produce the activity of the star, we have to find some way of actually looking beneath the surface of a star. And what we'd like to do is build up a detailed portrait of what the inside of a star looks like. And we now have a way of doing that. And we can do that because stars resonate just like musical instruments. So we can literally sound stars. And this is the only way we have of actually building up a picture, a detailed picture of what the inside of a star looks like. So we literally are here talking about the music of the star. So where do these resonances come from? If we think about the analogy of a musical instrument, if you play a wind instrument, say an oboe or a clarinet, you blow over the reed at the end of the instrument. The reed vibrates, it sets up changes in pressure in the air. Those are just sound waves. The sound waves are trapped within the body of the musical instrument, and they set up what we call standing waves that make the instrument resonate at its natural harmonics or overtones. Now, essentially the same thing happens in a star. So the image on the right here is a cutaway of the inside of a sun-like star. We've got the bright region at the center of a star like the sun, where we've got its nuclear fusion reactions taking place. But the orange part in the outer layers of the sun, this is where energy is being transported by moving hot parcels of gas from one place to another. We've got gas that's moving around, and very close to the surface of the star, these parcels of gas are knocking into one another. That's creating changes in pressure in the gas, and that's making sound. So stars make sound naturally in their interiors, and even though a star is a big ball of gas, it doesn't have solid edges like a musical instrument. It acts as a natural cavity to trap the sound, and we get standing waves set up just like in a musical instrument. And because a star is not a solid body, those compressions and relaxations of the sound waves make stars do this. So we don't literally listen to the stars. What we do is we're able to measure the gentle breathing of the stars, and all that information on the overtones and harmonics is coded into these gentle pulsations. And by measuring the pulsations, the rate at which the star is breathing in and out, we can get information about the interiors of the stars. Now, this is something that we call helioseismology when we talk about studying these oscillations and the star is the sun. So believe it or not, this is a definition in the Oxford English Dictionary. And when we extend our observations to other stars, we call it astroseismology. So seismology here, because we're kind of looking at star quakes, astro here for stars. So what can we learn then from these resonances? So again, thinking of the musical instrument analogy, if we had two players behind the screens here, one playing a little piccolo trumpet, one playing a tuba, we'd all know who was playing the little piccolo trumpet with its high-pitched tones. We'd all know who was playing the tuba with its much lower-pitched tones. So the pitch of the notes produced is telling us something about the size and the structure of the instrument. Also as well, something about the air inside the instrument. If we flush that out and put helium inside the instrument, of course that would change the timbre of the instrument. Of course it would sound very different. And that's because sound waves move at a different speed through helium than they do through air. So we can apply those same ideas to our studies of other stars and literally build up a picture of what their interiors look like. We can build up a picture of how different layers inside a star are spinning and how they're evolving and shaping these magnetic fields. And hence we can better understand this first link in the chain, in this active chain that runs from inside the star all the way through to the Earth. Now, the observations that we're using, my own group here in Birmingham for many years has been running a network of telescopes that make observations of the sun. We have data now stretching back over 30 years. We've been using data from a NASA mission called Chaplin now for many years. Kepler finished its mission just a few months ago, but now we are using data from a new mission, a new NASA mission called Tess, the Transiting Exoplanet Survey Satellite. This was launched in April last year. I was very lucky to go to the launch. That's definitely my best ever work trip for sure. And the data that we're using here now are data on the very brightest stars in the sky. So from July this year, Tess is going to be observing the brightest stars in the sky that we can see here from Birmingham. So come the end of the year, you'll be able to talk to family, friends, and colleagues about the planets that Tess has discovered, and indeed you'll be able to point at some of those stars in the sky and tell your friends, family, and colleagues about the nature of the planets that have been discovered. So I hope I've given you insights on this new exciting science that we're involved in, and I'd like to thank you for listening today. Thank you.